Welcome back to Principles of fMRI. In this module, we're going to introduce the general linear model, which is the bread and butter workhorse of statistical analysis. In this module and the following series, we'll walk you through how to construct a GLM and how to use it for fMRI. So there are multiple goals in the analysis of fMRI data, and they include localizing areas activated by a task or in relation to a process of interest, determining networks corresponding to brain function, functional connectivity and effective connectivity, and making predictions about psychological or disease states or other outcomes from functional imaging data. All of these can be handled in certain ways in the general linear modeling framework. So in terms of situating us and where we are in the whole process, we are here in the data analysis portion. And to give you a little bit more detailed view, an overview of the GLM analysis process, it's typically a two-level hierarchical analysis, and we analyze within subject effects in an individual by individual case. That's the first level. And secondly, we do analyses across subjects or across groups in a group analysis or second level analysis. We can do this in stages, and that's one approach, a common approach. Also, hierarchical models combine both those levels into one integrated model. So where we are in the processing stream, and the steps are, first, design specification or building a model. Secondly, that model is combined with real data and estimated, and effects are estimated at each voxel. And contrast images are calculated. We'll talk more about those later. Those are combined with images from other subjects into a group analysis. And then finally, we can make inferences about the areas that are activated in that group and localize them anatomically, talk about them. So let's first introduce the GLM family of tests. The general linear model approach treats the data as a linear combination of model functions, predictors, plus noise or error. So you can think of it as breaking the data up into the part that I can explain with a model and the part that I can't explain. These model functions are assumed to have known shapes, the simplest one being a straight line. But their amplitudes, or the slopes, are unknown, and those are what need to be estimated when I fit the model. I'm not limited to straight lines. I can also fit smooth, pre-specified curves or other functions, and we'll look at more examples of that later on. The GLM framework encompasses many techniques in fMRI data analysis, and also data analysis more generally. So chances are you've used some version of this in your research before. Let's look now at the entire GLM family. Well, many of you might be familiar with simple regression, one outcome, one predictor, or with ANOVA, analysis of multiple categories. And those are both instances of the general linear model. So they fit within the broad GLM framework. And in fact, they're instances of another subclass of the general linear model, multiple regression, which is a case where you have one outcome and multiple predictors. And in fact, any analysis that I can do in an ANOVA framework, I can do that exact same ANOVA analysis in a multiple regression framework. So those are actually interchangeable at a mechanistic level. They're all examples of the GLM. And more broadly, multiple regression is an instance or class of instances of the general linear model more broadly. And that encompasses models like mixed effects and hierarchical models, time series models with autoregressive components to them, and other advanced tweaks like robust models, penalized regression models. Many of you have heard of lasso or ridge, those kinds of things. And finally, there's this broad category of generalized linear models where I can incorporate ideas of non-normal errors, different error distributions, and logistic regression is one example of that. So all these are instances of the general linear model. In many cases, there is a simple closed-form algebraic solution, so I can solve the equations and estimate that model in one step. And in many other cases, they require iterative solutions. So I have to alternate between estimating the model parameters and estimating the error structure, for example. So this is the simplest example, simple linear regression, one predictor, one outcome. And for our purposes here, we'll just talk about 4 stages that we go through. One is we specify the model. In this case, it's very simple. We posit that there is a linear relationship between the predictor and the outcome. That's the model, the simplification of this complex data into a compact form. Then we estimate the model. In this case, this means that we have to estimate the slope and the intercept of that model where it crosses the y-axis. Third is statistical inference. I'd like to test the significance of that slope and get a p-value, which relates to how likely is it that I've observed a slope like this under the null hypothesis that there is no actual true relationship, that the line is actually flat, plus noise. And finally, when I find significant effects, I want to make a scientific interpretation, which has to do with the meaning of this relationship. So this is another view of the GLM family. I think it's useful to situate us. All the GLM models are characterized by the use of one variable, which is a continuous variable, as the dependent variable, or the outcome. So one continuous dv, and depending on what the structure of the predictors are, then one is doing different kinds of tests. All GLM tests, all with the same fundamental linear algebraic equations. So if I have one continuous predictor, that's simple regression. If I have two continuous predictors, that's multiple regression. Let's say I have a categorical predictor with two levels, male or female, and that's what I'm using to predict the outcome. That ends up being a two-sample t-test. If you have a categorical predictor with three or more levels, basketball players, football players, baseball players, and then the outcome might be memory, score, performance, that's a one-way ANOVA. If I have two or more categorical predictors arranged in factors, that's a factorial ANOVA. And we'll look at examples of that later as we go on. Another important extension of the GLM is the case where we have multiple observations on the same people, or repeated measures. So all of these in blue here are repeated measures designs, and they involve essentially then correlations in the error structure. So if I test one person at time 1, time 2, time 3, that's repeated measures. And because I have multiple observations on the same people, then those observations are linked by the person. They're no longer independent from the other from all the other observations. Or sorry, from one another, I should say. So that's a repeated measures design. And if you have a within-person predictor, one within-person predictor, that's a paired t-test, time 1, time 2, two levels. If you have multiple repeated measures, time 1, time 2, time 3, time 4, we're doing a one-way repeated measures ANOVA. We can also use MANOVA to analyze such data. If I have 4 or more repeated measures organized in a factor structure, like for example, I might have a memory experiment where I have words that are highly imageable or not, and they're presented in visual or auditory modality. That's a 2x2 factorial design, and that's a factorial repeated measures ANOVA design. That's very common in functional neuroimaging experiments. And if I have repeated measures, the same, let's say, repeated measure structure, but now I start to add between-person predictors, like a moderation of that effect, correlation with age or with performance, or with group status, patient versus control, then we'll just call that a GLM. And this illustrates that I can mix and match within-person and between-person factors and variables, and all within the same analysis framework. Another important extension is this idea of introducing other kinds of correlated error structures. So one example is time series correlations. Events that occur at one time point depend on what happens at time points before that. A quintessential example is the stock market. Things happen in the stock market and influence multiple time points. So each measurement across time is not independent from each other one. And we can use the generalized least squares framework with iterative models to model that kind of structure. This is the basic structural model for the GLM. And we'll first break it down and then show it in one compact equation. So up on the top here, what you see is y is the dependent variable throughout the course, and x is going to refer to predictors. And here I've got time point I, so I've got the outcome at time point I is broken down into beta naught, which is an intercept parameter that captures the average across time, constant across time, plus beta 1 times predictor 1, plus beta 2 times predictor 2, plus beta 3, and so on, for as many predictors as I have in the model. Those betas are regression slopes. When I estimate them, they become beta hats. We always use hat for an estimate. So this breaks down the model into the part that I can explain with the model, some combination of beta values or slopes times the predictors plus error, the residuals or everything left over. And the job then, when I estimate the GLM, is to solve for that beta vector, the series of beta naught, beta 1, beta 2, beta 3. And I do that typically by minimizing the sums of squared residuals, although there are other options as well. Now what you see on the bottom here is if I write that same equation, sort of messy equation, in matrix form, I get one very compact, beautiful equation. Y equals x times beta plus error. And let's take a closer look at this and break this down again. So y equals x beta plus error. That's decomposed into y is a column of observed data, and that's modeled in terms of a design matrix, which is the intercept plus all the other predictors. And the intercept is usually a constant value. In this case, it's just a column of ones, plus a column for each predictor or regressor in the model together. That's x times beta. Beta is a vector of the model parameters, all the regression slopes in the model, plus error, all the residuals or everything left over. So here's a non-fMRI example, and then later we'll map this onto the fMRI context. So in this non-fMRI example, I'm interested in whether exercise predicts lifespan. So the outcome, this is made up data, the outcome is going to be lifespan. A predictor is going to be exercise intensity level or amount, which is a continuous variable. And we'll introduce one other variable, which may or may not be important here. Let's say it's a covariate, and this is going to be gender, male or female. And so now I've got two predictors in my model. Let's look at how this works. Well, first, let's look at the data. This is an example of what the data might look like. Exercise is the predictor on the x-axis, and lifespan is the outcome on the y-axis. And now I've got the group of females and the group of males. And I can see that females and males are different. And that categorical variable is going to be an additional predictor. So I can look at the effect of exercise controlling for gender, gender controlling for exercise. And let's look at how this works then in terms of our design matrix and outcome. So the outcome data is the lifespan, which is a continuous variable distributed across the series of observations. In this case, observations are subjects. So this is what the lifespan data might look like. And that's decomposed into the part that I can model with the design matrix. And there's the design matrix itself. There's the intercept, which is a constant. Effective exercise is continuous. And now sex is included as a categorical variable. Because there are two levels, I can code that in regression with values of 1 and -1, for example, maybe 1 for female and -1 for male, or vice versa. And that looks like that as a predictor. And that design matrix is going to be multiplied by the model parameters, which I estimate when I fit the model, plus the error residuals, everything left over. So this example illustrates how I can do a rather complex design very simply using the general linear model. And this design would be called an ANCOVA design, analysis of covariance design in the traditional behavioral literature. So that's the end of this module. In the next module, we'll begin to map GLM onto fMRI data specifically. Done.